Good afternoon, everyone. I'm Michal Kulczewski. I work in Poznan Supercomputing and Networking Center as a senior specialist. I do hope you are enjoying the event. And now let's dive into the renewable energy sources. Why we actually model the renewable energy sources? So everyone probably is familiar with the climate change and the fossil fuels that are responsible for the CO2. So basically, the European Union, but also the whole world is trying to remove the fossil fuels and switch to the green energy coming from the wind farms, from the photovoltaic system, and also from the waterfall farms. And there's a directive in the European Union that aims to reach 32.5% of the gross energy consumption coming from the renewables by 2030. And already last year, this was achieved. 46.9% of the net electricity was produced from the renewable energy sources. So it clearly means we need to do a lot in order to efficiently use these resources. So there are quite different groups interested in having this model accurately, starting with wind and PV developers. They need to identify the best spots from the photovoltaic farms and also for the wind farms, and how to learn how to use it also in the most efficient way. And also the PV and wind plant operators need to estimate the energy production. This is crucial because, in particular for the photovoltaic systems, there are the stock exchange in which the plant operators and the DSOs decide what will be the price for the electricity. And in order to propose a proper price, they need to know in advance how much energy will be produced in the near future. But there are, of course, some challenges, and the most important one is the weather. So basically, there's no sun, there's no electricity coming from the photovoltaics. If there's no wind, there's no power coming from the wind farms. And in the end, all of us want to do the laundry, wash the dishes, and to be honest, we don't really care, at least most of us, don't really care about from which source the electricity is coming, either from fossil fuels or greenhouse, or from the green energy. They just want to do wash the dishes. But this information regarding the amount of electricity coming from the renewables is quite important for the DSOs, because in the end, the distribution system operators need to stabilize the grid in order to have enough electricity to reach each and every one of you. So in order to accurately model the renewable energy sources and the complex physical phenomena behind this, we need a multiscale simulation model. So what we are doing is that we are combining a weather forecast running on different scales, from global to regional, and in the end, there is this energy production model responsible for the electricity production forecast. But with these models, we need hardware, we need the infrastructure, we need the CPUs to run the simulation model, and also to limit the uncertainties coming from many different inputs, from the model parameterization, from the model itself. Again, we need like hundreds and thousands of CPU cores, and this is the reason why we are using the HPC and why the old fancy machines delivered by HPC GPU is quite crucial to us. So what we developed at PSNC is a REST toolkit. REST stands for Renewable Energy Sources, and this is an HPC suite for tackling the renewable energy sources challenges. We aim at different users, individuals, distributed operators, and also plant owners to use this code. And the most important feature of this code is that this is tailored to our non-HPC users. So it comes with a print interface, it comes with support for the ensembles, for the uncertain quantification, and it comes with transparent setup and execution. So the overall goal is to deliver the results to the user and not to bother with too many technical details. We have three different applications in this toolkit. First is the REST wind towards optimizing the wind farms and windmills suited for urban and urban areas. We have risk damages responsible for assessing the damages to the renewable energy sources infrastructure due to icing, due to excessive heat, or due to extreme wind, which is particularly important for the wind farms. And last but not least is the REST PV. PV stands for photovoltaic. So essentially, this service is to provide you with a forecast of electrical energy produced from the photovoltaic systems. So today I would like to give you an overview of our REST demonstrator. So again, this is to forecast the electric energy production from photovoltaic installation. We are using two models coupled together, running at different scales, from 4 kilometer spatial resolution up to 10 meter spatial resolution. The data we are using is openly available, including the OpenStreetMaps, the Prime datasets, EUDEM, GFS, also from OpenMeteo API. And why we actually do this? I mean, because you could argue that we could use available forecasts that are running at 25, 20, or maybe 520 resolution. The answer is that we do want to capture the local variabilities and the local phenomena that is not captured quite good with coarser grid resolution of the forecast model. And in order to validate and refine our approach, we have a photovoltaic farm installed near our headquarters. It's almost 1 megawatt peak of power, and this is used to verify the area model responsible for the electrical energy forecast. So the first step is to actually set up the application. This is done in the portal, so we have the graphic user interface. You select either the region of interest, or you can also pin to a point at which you have your photovoltaic infrastructure available. Optionally, you can provide all the details regarding the photovoltaic system. And if you are a more advanced user, you can also provide some details on either on models, the horizontal resolution, the time steps, so any factor related to the models. And you can also play with machine configuration, so select the amount of CPUs or GPUs you would like to use. But this is only for advanced users, because we see this toolkit as a tool to be used by non-HPC guys. So all these features are basically hidden, and the horizontal resolution time step is automatically calculated and proposed based on the region of interest. The next step is to actually run the model. So here we can see a screenshot of REST PV up and running. You have access to all previously run forecasts to see the details and to compare the results. You have the current forecast running, details on the HPC job. You have the overall progress. You have the stages. So basically, the stages the model actually up and running. No, we're keeping it. It's not 5 minutes. Okay, I'll speed it up 2 minutes. Then you have the stage progress and also the stage results. So speaking about the stages, here's the WRF model running up to 100 meters resolution. The goal is to detail the global forecast. Then you have the EULAG model that is running at least to street-scale level to even further detailed the results. And last but not least is the REST energy. So speaking about regarding the HPC, WRF requires like hundreds of CPUs, EULAG is requiring like thousands of CPUs. The REST energy should be able to run with less than 10 CPUs. So does does it look like the exascale? Not even close, right? But then we need to not forget to deal with the uncertainties. So we are running the ensembles, and for each we need to multiply the recurrent procedures like at least 10 times, if not 100 times, which gives us around 1 million CPUs to run a single job. And then you have to multiply this by the amount of time needed to actually deliver the simulation. So it can be minutes, it can be hours. So this is the reason why we do need a large-scale machine in order to provide accurate prediction. Regarding the state-of-the-art, the weather, the meteorological institutions are now providing some solutions to forecast the wind and to forecast the solar details for the sake of the photovoltaic systems. But in the end, this is still the weather forecast. What we are doing additionally is that we provide an AI-based model which actually tries to capture the relationship between the weather conditions and the amount of electric energy produced. So we are analyzing 12 different parameters, like direct radiation, the visibility, temperature, and so on and so forth. We are using PyTorch and Recurrent Neural Network, and we are able to quite accurately capture the amount of electric energy produced. So basically, the actual value is this blue or violet line, and the prediction is a red line. For your interest, the green line is direct radiation, which is the most important parameter with respect to the energy produced from the photovoltaics. Last but not least are the results. So in the end, once everything is calculated, we are providing the results to the users, especially the forecasted energy production, possible expected income, and the detailed energy production for each 15 minutes time step, along with some weather forecast. So just to conclude my presentation, what you saw is based on the QCG. QCG is the backend and the front end. So basically, it is responsible for doing the orchestration on HPC and provide the GUI interface. So we did not develop the GUI from scratch. We rather created a template with all the input boxes we need in order to run our application, and then the QCG do this for you automatically. So you can actually run any application with this portal. And I was also mentioning about uncertainty quantification and the ensembles. Also, the QCG comes with this feature, so you can run the ensembles and run the uncertainty quantification directly within the fancy tool. And with this, I conclude my presentation. I do hope I managed in time. Thank you. If there are any questions,